In this video, we are going to be adding, subtracting, and multiplying radical expressions. In our previous lesson, we were simplifying radicals and rational exponents, but now we are adding and subtracting them at first here. So in this first example, in order for you to be able to add or subtract radicals or things with rational exponents, they have to have the same root with the same radicand or number underneath. But then from there, it's basically just like adding like terms. So the coefficient for your first term here in example 1a is basically -1. You basically have -1 times the sixth root of 17 plus 9 times the sixth root of 17. So just like if you had a -1x plus a 9x, you would just simply add your coefficients. So the -1 plus 9 would be 8, and then just like the x wouldn't change, the sixth root of 17 doesn't change. Another way of thinking about this is if you were to look at these as two separate terms. So if you think of this as one term and you think of this as one term, both terms have a sixth root of 17 in common. So if you were to factor it out, what would you have left? Well, if I factor out the sixth root of 17 from both terms, I'm going to have a -1 plus 9. And again, the -1 plus 9 is 8. But since 8 is the real number, that's going to be in, or not real number, the rational number, that is going to go in front of the sixth root of 17. So basically that's the same thing as what we have here. So if I do the problems this way where I'm factoring out the common radical, I'm actually going to put it at the end rather than in front like we're used to with factoring. Okay, so the next example we have is one with rational exponents. So previously we learned that if you have the same base and if you were multiplying, then you would add the exponents. But we are not multiplying, we are subtracting. So we do have, again, if you think of this as one term and you think of this as one term, which it is, both terms have an 11 to the 1/4 power. So I could factor that 11 to the 1/4 power out, and then the 3 minus 9 would be put together in its own set of parentheses, and then 3 minus 9 would be -6, and then you'd still have the 11 to the 1/4 power. So notice that the -6 and the 11 cannot be multiplied together because the 11 has an exponent of 1/4, the -6 does not. So this is also the same as having a fourth root of 11. The -6 is a whole number. The 11 to the 1/4 power is a radical number or irrational number, so that cannot be combined with the -6. All right, so those are ones that already have like radicals or like rational exponents. In our next example, example C, these are not the same, so we need to simplify one or the other in order to get the 7 to the 1/3 power here from this 56. Well, it just so happens that 56 or 7 is a factor of 56. So in this first term, the -5 is already a whole number. I'm going to put that on the outside, but I'm going to factor the 56 to the 1/3 power into 8 to the 1/3 power times 7 to the 1/3 power. So if I were to multiply them back together, because they both have the 1/3 power, I would get the 56 to the 1/3 power. However, now we can simplify this 8 to the 1/3 power because that's the same as a cubed root of 8, and the cubed root of 8 is 2. So then you have to multiply that 2 times the -5 that was out front, and also by this 7 to the 1/3 power. So the -5 and 2 are your whole numbers. They can be multiplied together to get -10, and then your 7 to the 1/3 power cannot be multiplied with that -10. Now that we're done with that first term, the second term we can bring down. And now you can see that they have the same radical, or the same 7 to the 1/3 power. So because these are the same, you can add the coefficients. So the -10 plus 6 is -4, 7 to the 1/3 power. And that's it. All right, so the next one here now, we have 3 terms. So we've got a fourth root, so we're looking for perfect fourth powers. So if you forgot what some of your perfect fourth powers were, go back and maybe make a list. 2 to the 4th power is 16, which means the fourth root of 16 is equal to 2. 3 to the 4th power is 81, which means the fourth root of 81 is equal to 3. So 16 and 81 are perfect fourth powers. We could continue this with 4 to the 4th power or 5 to the 4th power, but 16 and 81 I think are all that we're going to need for this problem. If you look at your middle term, you have a fourth root of 3. 3 is a prime number, so this middle term probably cannot be simplified. So it's most likely that these will be factored into fourth root of 3 times fourth root of something else. So the first term you have a 2 already. And then the fourth root of 48 can be factored into a fourth root of 16 times a fourth root of 3. That fourth root of 16, just like we saw up here, is going to become 2. When you multiply that by the 2 that's already out there, you're going to get 4 fourth roots of 3. So that's what you get from that first term. Your middle term, like we said earlier, cannot be simplified because 3, that's not third root, fourth root, because 3 is a prime number. So that's just, you just bring that down. And then the last one, let's pick green. This last one, you have a 7 out front, and the fourth root of 243 can be factored into fourth root of 81 and the fourth root of 3. 81 times 3 does equal 243. And up here we saw that the fourth root of 81 does equal 3, so this becomes 3 times your positive 7 will give you a positive 21 fourth root of 3. So now that we have the common radical, we can then combine our coefficients. So the 4 minus 5 plus 21. And like I said, it's kind of like factoring out that fourth root of 3. But of course, we want to combine your 4 minus 5 plus 21. 4 minus 5 is -1, plus 21 is 20 fourth roots of 3. And that's your simplified answer. Okay, so the next couple examples we have variables. So your variable, just like with the regular numbers, you need a perfect fifth power to reduce here. Well, these two are very similar. The fifth root of x, since x is not to the fifth power, or it doesn't have any 5 factors of x, we cannot simplify that. So the first term here, we're not going to be able to do anything with. But the second term here is a little bit more interesting. This fifth root of -x, we can factor into a fifth root of -1 times a fifth root of x. And then you have this positive 2 in front. So the fifth root of -1, you can take negative numbers to an odd root. The fifth root of, or any odd root of -1 is -1. So when you multiply the 2 and the -1 together, now you have a coefficient of -2 fifth root of x. So you've got 6 fifth root of x minus 2 fifth root of x. When we subtract now, we get 4 fifth roots of x. And there's your simplified answer. The next one we have is has 2 variables in it. The third root of p squared cannot be simplified. So this first term we're going to leave alone. But this second term we are going to have to simplify. I'm going to simplify this off to, well, I guess let's do it here. So I'm going to separate this into the sixth root of n to the sixth times the sixth root of p to the fourth. Well, the sixth root of n to the sixth root and sixth power reduce, and you just get n. Our negative is still in front, so we can make it a -1 if we'd like. But then if you look at the sixth root of p to the fourth, it is not exactly the same as what we have over here. But using some of the rules from rational exponents, and radicals, you should be able to recognize that the third root of p squared is actually equivalent to the sixth root of p to the fourth. So let's just kind of take this sixth root of p to the fourth off to the side and rewrite it as a rational exponent. So the sixth root of p to the fourth is equivalent to p to the 4/6 power, 4 being the power and 6 being the root. The fraction 4/6 can be reduced to 2/3. So now if I rewrite this, now that I've simplified this, I can rewrite it now again as a radical. 3 is now my root and 2 is now my exponent. So as you can see, the sixth root of p to the fourth now is equivalent to the third root of p squared. So now we do have like terms. If you notice, both terms have an n cubed root of p squared, n cubed root of p squared. So if we factored out the n cubed root of p squared, we would have 16 minus 1 to put together, which would give you 15 n cubed root p squared. So that one's a little bit trickier because we have to use some of but it's convenient to be able to go back and forth between your rational exponents and your radicals in these problems. The rule, though, is if you start a problem, if the problem starts with a radical, then you should end with radical expressions. If your problem starts with a rational exponent, your answer should have a rational exponent. So again, I'll say that again. If your problems start off with radicals, then your answer should have radicals. If your problem starts out with rational exponents, then your answer should have a rational exponent. You may temporarily go between the one and the other, like we did here. We went from the radical to the rational, but then we went back to the radical because that's what we started with. So I do not want to see your final answers written in a different format than what you started with. Hopefully that makes sense. All right, and these two examples are going to be the last ones that we're going to do today. So now we are multiplying. So when you're multiplying, just like when you're multiplying variables, if you have 2x squared times 3x to the fifth, when you're multiplying, it doesn't matter if these are the same or not. You just multiply the coefficients and then you would add the exponents and you would get 6x to the seventh. Okay, so this is just kind of a review, but here we have a little bit different situation. We have square roots, but we are multiplying. So if we don't have a coefficient, we could put a 1 there. 1 times 2 would just be 2 in front. But as long as these roots are the same, you can multiply them together. So the square root of 21 times the square root of 14 would give us a square root of 294. But then we have to simplify this square root by finding a factor of 294 that is a perfect square. So if I go through my perfect squares, 4, 9, 16, 25, 36, the first one that is a factor of 294 is 49. So The 294 is going to factor into 49 and 6. The square root of 49 becomes 7 times 2 then is 14 square root of 6. So I'm actually going to show you another method of simplifying these, because multiplying these numbers together and getting a larger number that you don't know what the factors are might be a little bit more difficult. So I'm going to show you method 2 here. So method 2 is, I know that I can put all of this under the square root. So the 2 in front is going to stay the same. But rather than multiplying 21 and 14 together, I'm going to factor 21 and 14. So 21 can be factored into 7 times 3. 14 can be factored into 7 times 2. So if we look here, we now have 2 factors of 7. So I could rewrite that as a square root of 7 squared. And then I would still have the 3 times 2 that are not perfect squares that can stay underneath. And then we have this 2 out here. So the square root of 7 squared then, just like the 49, 7 squared and 49 are the same thing, becomes 7. Multiply it by the 2, you get 14. And then the square root of 3 times 2 becomes square root of 6. So we still get the same answer. We just didn't have to work with that really large number. So what method you choose kind of really depends on how large these numbers are. All right, so the last one we're going to do in this video is a cubed root of 18 times a cubed root of 6. So there are no coefficients in front to multiply. So I would just multiply the 18 times the 6, and I would get 108. Since it is a cubed root, I need to look for perfect cubes. So I can try to divide by 8. 8 is a perfect cube. 2 to the third is 8. But it does not go into 108. The next perfect cube would be 27, because that's 3 to the third power. And 27 is a factor of 108. So the cube root of 27 and the cube root of 4. 27 times 4 is 108. So again, if you multiply this back together, it will equal what you started with. The cube root of 27 is 3. And then you've got this cube root of 4 that cannot be simplified. That is your final answer. Again, using that second method, method 2, rather than multiplying the 18 and the 6 together and getting 108, I'm going to factor 18 into its prime factors. So 18 is 9 times 2, and 9 can be factored into 3 times 3. So the prime factorization of 18 is 3 times 3 times 2. The prime factorization of 6 is 3 times 2. So now when we look at all the prime factors together, you can see again that you have 3 factors of 3. And that can be written as a cubed root of 3 to the third. And then the cubed root of 2 times 2 would be left under the radical. The cubed root of 3 to the third reduces, you get 3. The cubed root of 2 times 2 simplifies to a cubed root of 4. 4 is not a perfect cube, nor does it have any factors that are. So that is our simplified radical. Again, we get the same thing. It's just a matter of which method you think is easier.